Sorry, sir.
Yes, go ahead.
Sir, I have load shedding now from 2 to 4. So if I ever leave the room, just know that I have load.
Okay, Sean, no problem. Yeah, we'll record and upload the sessions. I understand load shedding might affect some of us. Okay, thanks. Okay, so of course, we've been developing the reactor energy balance, and we worked through all this, right? We applied the general energy balance and went all the way to the first law of thermodynamics, heat of reaction, enthalpy, and we started talking about applying that in a reactor. So we had done that in the CSTR, and there was an exercise we did on that as well. And if you look at this exercise that we did, I'd say it's a little contrived because it's quite heavily specified in terms of the number of temperatures and so on. But anyway, that was just to illustrate what we were doing here. But this is not such a natural way to do reactor design because you don't normally specify what exit temperature you want. Right. So, well, it's not the case you don't specify it, but in this case, we were able to solve this problem so easily. Right. And if you look here, it was as easy as this. And that's because we were given so many specifics about this question. And we were doing that because we wanted to illustrate how useful the energy balance was. And we found that there was this very close relationship between the conversion and the temperature. So when we allowed the reaction mixture to react, the temperature would change. So it would enter at T in, and as the reactants were converted to products, then that inherent energy change, right? So when A goes to B, for example, there's inherently a certain amount of potential energy. So let's just think about that simple example. So A going to B, I was teaching the second years earlier. So when A goes to B, A and B are molecules with different molecular structures. So their bonds and so on are arranged differently. And so the energy taken to form A is different to the energy taken to form B, even if they consist of the exact same atomic centers. So just the fact of them being arranged differently in terms of that molecule, that means you can think of it as a kind of chemical potential energy in each case. So because they are different, when A is translated to B, then there's a certain net energy change. And there isn't any other place to put it, right? That energy, let's say A had a higher energy than B. So for instance, let's say A was highly disordered and B was very ordered. Think about polymerization, right? When you form a polymer, you take many, many small molecules bouncing around like crazy in the reactor, and you form one long chain of those monomer units. So you're going from a highly disordered, high energy state to a much more ordered and lower energy state. So the molecules are that way. In terms of the molecules themselves, the state of order is different. But in order to accomplish this change in orderedness, right, to become such a long ordered chain, you have to release all that energy somehow. And the way that's released is as thermal energy. So those individual high energy molecules will go and knock onto something else and give up their kinetic energy there. And so the surroundings get hotter. So the molecules, just the fact, it doesn't matter that the same atomic centers may apply. Just the fact that they are more ordered in this case means that they must have lost a lot of energy. And there's no other place for that energy to go than the surroundings. So the temperature rises when we become more ordered. So that's an example of an exothermic reaction. And so those are the things that run through our mind when we see an equation like this, that we entered at a certain temperature, and now the contents are at a different temperature. And for that temperature change to occur, we must have converted a certain amount of the reactant. So that's how we look at this equation. And we can even see these parameters here, the heat capacities and the heat of reaction. Those are basically the factors that convert us from this energy change that is reflected in terms of the temperature changing and the energy change associated with this change in the types of molecules that we have. So that's how we read this energy balance. And so because there is this close relationship, in fact, it is the same thing. It's just a statement about the energy. So because of this, it is the case that we can actually determine what the conversion was just by knowing the temperature. So that's what we were emphasizing in this problem. But when we design a reactor, we are typically thinking about the reactor volume, and we are concerned about the reaction rate. So you see here, there's no reaction rate at all, right? We are able to determine something about the conversion of our species, even though we never once wrote down anything about the reaction rate here. I think that's pretty amazing. But anyway, what we do want to do is work with the reaction rate. So what we want to look at in this tutorial now is a more natural way of designing reactors, right? Normally, we don't get this type of information in a reactor design. So let's have a look at the questions that we have here. I didn't get a chance to upload this, so just please work from the screen here. I think in the breaks, I'll just PDF this and put it on the Dropbox folder. So the first question, it says we have a CSTR and this is the reaction. I just want to check the chat and all that. Okay. So it says here, we have the CSTR. It's an elementary reaction, and this is the kinetic rate constant. Well, that's its relationship with temperature. The feed is pure A, and the temperature is this, and the concentration of that feed is this. So the heat of reaction is also given here. So if your volume is this much, what's the conversion? So this is, as I say, a bit more of a natural type of reactor design. We know what kind of feed we have. So we are receiving some raw material from somewhere else on the plant, and it's coming out of something at some temperature and some concentration. And we have this reactor, and we want to know what's the best we can do in terms of accomplishing some conversion there. And this problem is now more complicated than we saw in the isothermal reactor design, because now we have a temperature to think about, right? Before, we used to just say, boom, here's the kinetic rate constant. It was some number. Now it's a function of temperature. And so we know that the temperature is also going to change due to the reaction. So in this case, we want to evaluate the reaction rate given these specifics. Okay, so this is the first tutorial. We'll be doing these two questions in this tutorial, and then we'll have a lecture in between, and then there's another set of questions we'll be working through later. So start with this question, and yeah, so take 10 minutes and work through this, and we can talk about it further. Any questions or comments before we start with that? So I was telling the second years, and I think I got an email about it just now, how do you teach online in a tutorial? How do you do tutorials like this? So yeah, we'll just be pausing in between, inviting you to try the question, and then we'll talk through it after that. Okay, please go ahead.
So we need to see the question.
Oh, of course. 1 second. Well, I'm just going to copy this to a document and post it to the course website, okay? I don't even do that.
So,
Yeah.
so I just wanted to ask, when it came to that question here, k, where it's equal to 0.0258 times the exponent, all that, is that 0.0258 the value of a, and that negative 17368.42, is that the e value?
Yeah, so this is the pre-exponential factor, a. And then remember the standard form is ae to the minus e over rt. So E is not minus this E. E is the energy. So E is always positive. So yeah, this is the E. That's right.
Okay, thank you.
Right. What I'm going to do is just print this. So if you ever want to print out these things, just go to read mode and print the save to PDF. And let's do this. Let's do this here. Okay, so give me a second. I'm just going to save this PDF to the Dropbox folder. Okay, I've saved it to the Dropbox folder. I think let me also upload it to the Learn 23. Okay, so you should have access to the questions there. Just scroll right to the end. Look for exercises 4.1 and 4.2.
So,
Yep.
Do you mind if I ask you for help with something? It doesn't deal with this section. It's actually something that deals with chapter 2, real quickly.
Okay, there's just one thing I noticed, which is a missing heat capacity for component A. So for this exercise 4.1 and I think 4.2, everyone please use a heat capacity of 50 joules per mole per Kelvin. Okay, I'm just going to type that in the chat. Okay. Okay, please go ahead.
Yes, I was hoping if I could ask for your help with something that deals with chapter 2, ideal reactors.
Yeah.
So it's actually exercise 2.1.
2.1. The general balance. Okay.
Yes, generalized. It deals with exercise 2.1. I believe it's question 1 or something.
Yeah. What's
So
the productivity of the reactor? That one.
yes, sir, that one. So I wanted to know, what is that A value? You know where it says K times A into A times L plus half B times L squared.
I'm not seeing that. 1 second. Oh, so you mean in the solution?
Yeah, in the solution. It says there Ka. What is that A value?
Well, A and B, if you look at the second line in the solution, well, it says, let's write the concentration profile as Ca of Z is A plus BZ. So if you read the original
not
question,
that. No, not that. I know that small a and B value. I mean that capital A.
capital A, see the capital A. Well, that's the area. So this is a tube. It says it's, yeah, it's a reactor. So yeah, here it says it's a 4 centimeter reactor. So that refers to the diameter of length 1.2 meters. So yeah, you're given the diameter and the length, and you need to integrate across the tube to get the total reaction rate there. So your capital A is your cross-sectional area. And you see, if you look at that, the reaction rate, it's the integral of the local reaction rate with respect to volume. So you add up the reaction rates throughout the volume, just like we did in the generalized mole balance. In fact, that's what it's trying to illustrate. If you look at the generalized mole balance, the total reaction rate is the integral of the reaction rate. So here we are just changing the variable. The integration variable is the volume, whereas the geometry we have is of a tube with a length. So we are converting the dV into an AdZ. So A is the cross-sectional area and Z is the axial distance.
And so the formula for area, for this case, would it be pi dl?
No, the cross-sectional area is pi r squared, so the diameter over 2. Yeah.
Oh, okay. Pi r squared. Okay, thank you.
Okay, sure. Any other questions or comments there? Okay, so let's start having a look at, I'm just navigating there. Okay, feel free to tell me if I'm not giving you enough time. Yeah, it's a bit hard to pace myself with this, doing a tutorial online like this. But here is the solution. So Well, let's just think about the problem first. So we have a CSTR, and that's the balance, and it's that's the reaction equation, and that's elementary, and we have the temperature dependence. So we have pure A coming in, and all the specifics about the reaction and the volume is given. So what we need to do is estimate the reaction rate. Remember, it's a CSTR, so one reaction rate will apply. The complication for us is that we don't know the temperature in the reactor, nor do we know the conversion. That's actually what we're trying to determine. So we only know the feed temperature of A. So it looks like we have two unknowns in this problem. Fortunately, we also have two powerful balances. So we have the energy balance. So that's how we can think of this, the energy balance. And this is, of course, in the adiabatic form, where we don't have a jacket or a heating coil or anything. So the so-called adiabat, that's our energy balance there. And we know we've got the material balance on a CSTR as well. And there are a number of assumptions here: perfect mixing, equal flow, steady flow, and all of that. So there's our material balance, and there's our energy balance. And we are told this is pure A. So if it's pure A, this general thing, which is theta I CPI, this can be written simply as CPA. And we saw that last time, right? In the example we did last time, we also had the pure A. So it's as simple as that. And then the heat of reaction is simply given to us. It doesn't really say whether that's the standard heat or anything. Just it says that is the heat of reaction. So we'll just assume that it's the right heat of reaction in the range, or it's the average heat of reaction that's good enough for us to use, just like so. So that's the heat of reaction. And then the temperature difference here, T minus Tn, where we don't know this T. We don't know what the eventual CSTR temperature is. So now at least we have a relationship between X and T. And we know that we are used to working in terms of conversion in our material balance. So we'd rather rewrite this in terms of T. We'd rather get rid of the T. So if we just make T the subject of this formula, then it looks like this, okay? So we park that result for now, and then we head over to the material balance for the CSTR. And we can see here, we might as well rewrite the molar flow in terms of the volumetric flow rate and the concentration. And then, of course, we've got volume and volumetric flow rate here. So we can rewrite this as RA tau equals CA in X, right? Which is what we say here. So CA in X equals RA tau, right? Consumption rate, so minus there. And then the reaction rate, of course, we said it's elementary. So it's going to be kCa squared. So we substitute for the reaction rate here with kCa squared. And of course, we have to expand this. We have to acknowledge this K is a temperature function. And fortunately, we are given that function explicitly. We are given all the constants here. And quite often in reaction engineering research, getting these parameters in particular is a significant piece of the work. All right, but we are given those. So this is fully specified as a temperature function. And then, of course, the concentration, Ca squared, we can rewrite as Ca in squared times 1 minus Xa squared. So that's what we have here. And basically, we are ready to solve this balance because, number one, we can get rid of this temperature by substituting for this temperature here. So we just replace T by this. And you see, these are constants. T in is given in the problem. So we are told we are feeding at this temperature. So T in is known. Heat of reaction and heat capacity are known as well. So everything is specified except for T and X. And now we've gotten rid of the T. We are writing this in terms of X. And so this is in terms of X now. So we can substitute that in our K of T. So for this T here, we can rewrite it in terms of X. So if we look at this balance now, everything is in terms of x. On this side, we've got an x. This Ca in is a given constant in the problem. We've just talked about this. This is in x now. That's a given constant, Ca in. And there's another x. And this tau here, we do need this tau. I may have neglected that. Just use a tau of 20 minutes there, please. So I'll just add that piece of data as well.
So what did you say that heat capacity value was again?
So it's here in the chat. Oh, I guess you can't see my chat here, but it's 50 joules per mole per Kelvin. Okay. Oh, I see. Because you messaged me last, Arkaj, it's only going to you. Let me paste it to the room. 1 second. Why didn't you all complain? Hey, you didn't post the heat capacity yet. So that's that. Okay, so you'll find in the chat, heat capacity of A is 50 joules per mole per Kelvin, and tau is 20 minutes. Okay, so with all that specified, we now have a single equation in X, and we can solve it. This should be an XA, by the way. Right, so we can solve this equation for X. You can see it's quite a nonlinear equation, right? Besides the X squared here, your function here is an exponential, and it's 1 over t, and t itself is, well, it's linear in X, at least over here. But overall, this is quite a nonlinear equation. So I wouldn't suggest trying to solve this analytically, as they say. What you could do instead is just draw the line x to Ca in times x for the left-hand side, and just use a couple of points, try 0.1, maybe 0.1, 0.5, 0.7 for x, and evaluate the right-hand side. And so you'll get one curve for the left-hand side and another curve for the right-hand side, and where they intersect, you'll have your conversion. So I'm just saying, you probably want to just do this numerically quickly instead of trying to actually solve such a nonlinear equation. Okay, but that's the concept. Any questions or comments on solving this problem?
I'll say, can you hear me?
Yes, Freedom, go ahead.
I just wanted to clarify on that part of those two x. There is x and xa, right?
Yeah, this should be xa.
Oh, it should be xa as well, meaning it's one variable.
Yeah.
The one we're looking for.
Yeah, let me cut the xa out from this one. That's the only one where I wrote xa. Yeah, sorry about that. Let me just get rid of that. That's non-iso. Nope. This one. So here, xa. See, this is LaTeX. I think it's that one, right? Okay, so that.
What do they mean on? You see, on that explanation, they're saying we should trying the value of x. It's just that I can't see, but there is that explanation on that answer. Can you got
Yeah. So what I'm saying here is, I was saying that it's very non-linear. This equation, this side is linear, but on this side, number one, you've got the squared, which is not so bad, but here you've got that inverse exponential dependence, and you have to substitute this equation in here. So this is quite non-linear. So I was suggesting that you just go ahead and plot a few points. So for the left-hand side, you can just do something like this. You can just you could just go and draw. Yeah, so you can just take some points. So on the left-hand side, you can see it's a straight line in X. So where are we? You can see on the side CA in X, you can just multiply CA in, which is given, and plot that against X. So as you do that, you'll get something like that. So this is the left-hand side. And then, oh goodness, left-hand side. And then for the right-hand side, you just stick in some X values. So you choose a value like, say 0.1, 0.5, 0.7, evaluate this, and similarly here. So the entire right-hand side is also only a function of X. So you can pick 0.1, 0.5, 0.7, and so those will give you some numbers on the right-hand side. And so you can just go ahead and it will be some nonlinear curve. And then you can just read off the solution from there. So that's good enough for a quick estimate in a probability. Yeah.
So what is the label on the y-axis of that graph?
There's no, this is just the result of, so for the left-hand side, whatever numbers you get, you just stick those numbers in there. And the right-hand side, I mean, we could try and think about what it actually means if we look at the equation. I guess if you look at these, yeah, that's the amount that was converted. But we don't actually care about that. We just want to try and solve this equation. So whatever the numbers are, we just want to know where they are equal, then that will be the solution of that equation.
Oh, so it's like trial and error method, basically.
Yeah. And a bit of interpolation. So you see, to solve a lot of the problems in this course, a lot of them are nonlinear and all that. So just these quick and dirty methods just to get you to a ballpark answer. And you might think this is just because, for a test or exam, that's what we do. But even in real reactor design, they often do these kind of back of the envelope calculations to hone in on a useful solution. Okay.
Say one last question. Say for CAN, is it safe to use that concentration given, or yes, you see that concentration given in the equation?
Yeah. So it says it's pure A.
Exactly.
Yeah, it says it is pure A, so we can assume that this concentration is not just a total concentration or anything. It is the concentration of A. Yeah.
Oh, okay. And I was confused. Thank you, sir.
Okay, thanks. Any other questions or comments there?
So I just wanted to know, is this the type of question we could expect in a test situation?
Sure. I've got no problem with a question like that. Yeah. Can I ask, why do you ask?
No, I'm just I just wondered because so I understand either way we are gonna have to do these types of questions like in a tutorial or anything. But the reason I'm asking is because, well, of course, these types of questions would take a lot of time and it'd be quite tedious. And we might all be using different initial values and stuff. Like we might not all use that same X value or that same whatever value on the left-hand side or on the right-hand side. So our answers will be quite different.
Are you referring to this Publon Press thing?
Yes, this exercise 4.1, could we expect a question like this in a test or exam situation?
Yeah, I'm trying to ask you, are you saying your answers will be different because of the numerical nature of the solving, or because of the way the question is generated on this page?
No, well, basically what you've said first, like we could all be using a different initial value of our own, and our answers might not all be the same.
Yeah, look, that's accepted in reactor design. There's so much free play. We only have a few guiding principles. So that's why when marking, you have to look at each proposal on its merits. Yeah, that's part of the approach. That's right.
Okay, thank you.
Thanks. Okay, any other questions or comments? Okay, then for the next one, it's almost exactly the same question, right? You can see the same reaction equation. You are again given the temperature dependence of the rate constant. You're given the inlet temperature and concentration. Use the same heat capacity that we said. Well, we already said use it, and now they are talking about a cross-sectional area and the length, and we want to know the conversion in this case. So it's a PFR now. Everything else is almost the same, except we are given more dimensions. So please go ahead and propose a solution for this one. Okay, was that enough time or? Okay, maybe let's give it another few minutes. Okay, let's talk about how to solve this one. So in the case of the PFR, we have quite a different problem in spite of everything else being almost the same. And I know the numbers might be a bit different, but in terms of the reaction, in terms of the chemistry of the system, it's pretty identical to the first one. But in the PFR, we have, of course, the problem that now our reaction space behaves differently from one point to the next. So let's make a quick drawing about that. So here's our PFR. And now, well, let's draw the CSTR as well. So in the earlier CSTR case, the whole reactor, of course, is perfectly mixed. So the same temperature applies everywhere. And so there's one temperature and there's one concentration everywhere. So there's one reaction rate. In the PFR, of course, we've got a variety of reaction rates, and we knew that before. We knew that the conversion and hence the concentration was changing across the reactor. So we knew we had to integrate to get the overall conversion or the performance of the reactor. So in this case, we now also have an energy balance. So we also have the temperature varying across the space. So we do have to modify our design approach in the case of the PFR. And we had spent quite a bit of time talking about how to do that when we were adding heat. And let's just look back at our development for this. So going here to energy balance in a PFR. So we had done all this development. And here we had the adiabat. And we have here that the addition of heat term and so on. In this case, we did do all this work about a jacketed PFR. So we said, if we have a jacket and there's heat exchange between the reactor and the fluid in that jacket, then we had to go and differentiate, and because we needed to evaluate, we needed to reevaluate the heat transferred between the reactor, the local temperature in the reactor. And so there was a fair bit of work to do, and we had to integrate forward and so on. So the moment you have a jacket, you have to do all this extra work. In the problem we're looking at now, it is a PFR, but it's not jacketed. It's just that the temperature does change. So if that's the case, if we don't have a Q dot term, and of course, we're not really worried about shaft work in the case of a PFR, then only this applies. And we can say this equation then generally describes the relationship between conversion and temperature, right? The relationship is much more complicated if it is jacketed. If we are adding heat, then we can't see that relationship so directly. But if it's not jacketed, then we can just use the same equation. So even though we just used this for the CSTR, because this relationship is fundamental, right? Remember what we said just before this. We said it's the relationship between the chemical potential energy and the thermal energy, the state of disorder, right? Now, that is all quite fundamental. That's quite a fundamental way to look at the translation between thermal energy and chemical potential energy. So it's fundamental enough that it's independent of the type of reactor. So I'm trying to say that's why this form is still valid in our PFR. In the absence of the addition of heat, the same relationship does apply. And so we can still use this relationship between conversion and temperature. And so that means in our balance here, our reaction rate, the temperature dependence of our reaction rate, we can still use, we can still substitute that temperature dependence through this energy balance here. So it turns out this, this can be solved as a single equation. In the case of a non-adiabatic PFR, you can see then we have to concern ourselves with how the heat transfer goes between the two fluids. And so there we will have to integrate the temperature variation and the conversion variation across the reactor. But when it's adiabatic, then it's good enough to integrate just this one equation. So just to outline that solution a bit more, where's our scratch pad? Okay, so we said this balance. We have this balance. So F A in dx dv equals R A. And in this case, that's equal to K, which we're going to acknowledge is a temperature function. And temperature is a function of conversion. So it's K times CA squared. And so this is equal to this is going to be CA in squared times 1 minus x. Yeah, we're using x, right? Not XA, x, like that. So that's our balance. And if you look at this, this is nothing but an ODE, a single variable ODE. So this is pretty straightforward. So FA in is defined, well, CA in, and yeah, we'll need to specify an FA in. But if you look at this, you've got yeah, your function for K is given, CA in is given, and your variable is X. So we can step forward and integrate this. I just wanted also to translate this. So you see the problem is giving us a diameter and a length. So we'd rather work in terms of the length Z here. So we can say this dV, we can rewrite that as an A dz. So we can take out this A, the cross-sectional area, which is simply given, right? I think the way we posed this problem, we didn't specify a diameter or anything. We just said, boom, here's the area. Okay, so that's there.
The charger.
Okay, sorry, 1 second.
I need to.
Sorry about that. So yeah, we've got, we can express, instead of working in terms of a volume, it's an area and an axial distance. And so this is a constant. And if you look at that area, that's just given to us in the question. Yeah, it's, well, this is not, let's see, the tutorial is here. And in this problem, we are just told the cross-sectional area is about 5 square meters. So this is a constant, and then we can rewrite this as, we can say xi, xi plus 1 equals dx dz dx dz times delta z, and then plus xi. Right, so this is nothing but, well, I mean, some people call this Newton's formula and all that, which is a bit too formal a way to think of it. The way to write this equation is just to remember, well, if I know dx dz, if that is approximately xi plus 1 minus xi divided by delta z, then if I just solve for xi plus 1, right, then I'll multiply delta z by dx dz. So we've multiplied it here, and then we have to add this on the other side, and then we'll get xi plus 1. So it's just, if you like, another way to express the derivative approximation. So you can just step forward, right? You can start from your initial condition. So of course we are entering the reactor with a 0 conversion, and then we will need at the inlet point dx dz. So we can just look at this equation. We know that at the inlet x equals 0. So we can say x is 0 here, and we can apply x is 0 here and calculate the temperature and evaluate K. And so that gives us FA in dx dV. And then we divide by FA in and by the area. And then that will give us a number for dx dz. And then we have to choose a delta z. And typically, I would recommend just take 3 points. Don't plan to give me a super accurate answer. All you need to do is show that you know how to do the integration. And then, of course, in the first point, xi is 0. So you step forward to get your x1. And then in the next iteration, you now have an x1. You stick that x1 in here. So this time you use a different x here and here. You'll get a different dx dv. Then you step forward to x2 and so on. The way to check whether your solution has converged is to halve your step size. So your delta z, if you halve it and then recalculate and see that your solution is close enough, that's what you would do if you were doing this more serious, well, not seriously, but if you were if you were looking for an accurate solution. But here we aren't so much looking at that. Here we're just looking for method, of course. So that's how you would progress that solution there. Any questions or comments on that?
Yes, sir.
Sure.
I'm a bit confused on the. Can you go back to where you were driving that equation?
This one?
Yeah, the dx over dz. So is it okay if I assume that it is equal to that one all the times?
So here you've got dx.
I don't know if I'm...
So if you just move this across, right? If we multiply this on this side, if we make this a up here, so if we invert this basically, oops. If we just move this to the denominator, yeah, if we just take this on the other side, you can see dx dz here. So I'm just saying we got dx dz from your material balance, well, and your energy balance to an extent. So we know how to get dx dz. So given an x value, we are able to evaluate the right-hand side here and get a number for dx dz. So we just use that number. Then we choose delta z's as well. So if we are told the reactor is whatever, 2 meters or something like that, and we know we want to take, let's say 3 points, then we'll say, let's take 0, maybe 0.6, 0.6, and maybe 1.3 and then 2.0. And these are 3 steps, because although these are 4 points, that's one step, that's another step, that's the third step. So we are integrating over these 3 intervals, and the last one will give us the exiting conversion there. Does that cover it, Freedom?
Yeah, it covers. I was just confused on that. If a an area and coming to dx over dz, but I see. So meaning, in short, if I assume that dx over dz is equal to xi plus 1 minus it's xi, I think, over, I think it was delta z, is it fine?
I'm just trying to, okay. Say that again, please.
Okay, you see the last 2 equations there?
Yeah.
If all the times I assume it like this way and substitute it, then do the rest, is it fine?
If I didn't get what you...
Okay, basically you're saying dx over dz, it equals to what is on the right side?
This part.
No, the last part.
Oh, here. Yeah, well, I'm saying
Yes.
This is what this operation dx dz, that's the definition of your derivative, right? Your derivative is there's a change in x over a change in z. And of course, as delta z goes to 0, then this becomes more exact. But that's just the definition of a derivative. So I'm saying this derivative here is equal to this. So if I substitute this up here, or if I just rewrite it that way, then that's how I can evaluate xi plus 1. So given my current point, xi, I can use this to step forward and solve for xi plus 1.
Thank you, sir. It's clear. Thank you.
Right. So you've seen it in process modeling, right? When you did the Euler's formula with Dr. Mudley. So it's the same thing, like your Runga-Kutta methods. Well, 3PO, maybe you didn't come to that section yet, but you'll do it in detail there. So this is just, again, a quick and dirty way to integrate. There are more accurate ways to step forward, but it takes a bit more calculation. Just something that someone said earlier, it's that it seems like there's a lot of work, and it's tedious and so on. But actually, this is regarded as very quick. These are like back of the envelope calculations. You just stick numbers in here. It's just, 3 or 4 months, just a few numbers that you put into your calculator, get a quick derivative, step it forward. This is not supposed to take a long time. So, you might want to practice if your calculator skills are if you don't have enough speed on the calculator, so practice it, make sure you can solve these things quickly. It's not expected that this would take you a long time. Just in terms of the number, just in terms of evaluating the numbers, right? Okay, any other questions or comments there? Okay, then I'm not sure whether to pause for a break before we go into the next section. Okay, let's take 5 minutes. So let's be back. Well, let's call it at 3:15.
Sir,
Yeah.
so we can go into break, but I just wanted to ask for my sake, for exercise 4.2, is there no solution on Publon?
Yeah, I haven't sketched out my solution there. I will add that. Yeah, I'll add that in later.
Okay.
But
Right.
for now, what's here is I guess this is the solutions. So the similar thing to what's here will be on Publon a bit later.
Oh, okay. Thank you.
Okay. Okay, we're back. So what we want to do now is design our reactor system in the face of this energy balance, right, with the fact that the temperature influences the reaction rate and so on. And so what we want to develop is the reaction phase plane. So in other words, we'd like to have a handle on how the reaction rate is varying with both conversion and temperature, right? We've seen that conversion and temperature occur again and again in our designs. So we'd like a quick view of how the reaction rate is going to change with conversion and temperature. Something that we should be observing in the exercises we're doing is that, in a sense, we have some free choice. We can choose how big to make the reactor, and in effect, we are choosing what the exit conversions and temperatures are. And like we saw in the earlier design attempts, how big the reactor was did change what the productivity of the system was. So we'd like to create a reaction phase plane and be able to use that to develop our designs. So to do that, let's take a basis reaction. So we're going to take the reversible reaction here. So A goes to B and B goes to A. So that's reversible. So there's a forward reaction, and its rate is K forward, and it's first order in A, and the reverse reaction is first order in B. Excuse me. So our net rate of consumption, right, minus RA. Remember, RA is rate of formation, so minus. So the net rate of consumption of A is the forward reaction where A is consumed, and minus the reverse reaction where A is restored. So that's the net rate of consumption of A. And if we assume that there's no B in the reactor initially, then the amount of B that we have in the reactor, that must be due to A having reacted. So CB must equal CA naught XA. And then CA, we know we can write as CA naught 1 minus XA. So that's the reaction rate here. And we can say at equilibrium, right? We know at equilibrium, the net rate is 0. And so we have this, and you can see we can cancel the CA naughts here, and we're left with this. And then if we divide by KR, so let's say we imagine taking one of these across, and then if we take KF divided by KR, then we're left with XAE divided by 1 minus XAE. So it looks like that. And then let's define KF over KR as a KE, capital KE, equilibrium constant. So that's what we have. So looking here, KE equals XAE over 1 minus XAE. And if we imagine multiplying this out, if we multiply both sides by 1 minus XAE, and then we group out the XAEs. So you've got an XAE on this side, you can group out 1, and then take this one across there. Then on this side, it's minus KE XAE. So you take it across, it becomes plus. And so you can group out and you can show XAE equals this, right? So that's our equilibrium conversion. Our equilibrium constant, we can see, is dependent on these two. It's temperature dependent, right? So we know that we can use the Arrhenius expressions for KF and KR. And if we take their ratio, then that will give us a KE. So once more, if we just use an Arrhenius expression, imagine taking a series of points. So if we just draw it here, if we just take a series of temperatures and we just pick some values there. So just picking some values. Just picking some values here. So we can pick some values, some temperature values, and we can calculate Kf and calculate Kr and take Kf over Kr. Then that will give us a Ke. And then we can stick each Ke value in here, and that will give us an XAE. So in other words, on this temperature, so we are taking a series of temperatures, and then we are using that to calculate Ke. And then with that Ke, we can go ahead and calculate an XAE. And we may get a curve that looks something like this. So this is, let's say, an equilibrium line. And can you tell me, is this a place you want to be? So this equilibrium line, what does it represent to us? Right, we said we want to navigate our plane. We want to show our reactor design on this plane of conversion versus temperature. So is this operating on this line, is that desirable or not desirable? So maybe let's do the thing where we say hands up for that this is a desirable place to operate. Hands up if you want to operate your reactor on this line. Okay, and thumbs down if you don't want to operate your reactor on this line. Okay, so I've got 2 thumbs up. Well, we said this line was the equilibrium line, right? And let's look at that equilibrium. So, oops, where are we? Sorry, I'm a bit lost. When we wrote this here, so we found, these are the equilibrium conversions. So equilibrium, of course, is where our net rate is 0. So do we want a 0 reaction rate? Right? Does that help you answer yes or no? Right. So of course, we don't want a 0 rate. We want component A to react and give us a product. So already what we are seeing on this plane is a place we want to strictly avoid. We want to stay as far away from this line as possible because nothing is happening on this line. Our reactor is not giving us any product. So we don't want this equilibrium. We want to stay away from it. So we found this equilibrium line. Now what we can do instead then is consider reaction rates.
Sorry, I just wanted to ask, why is the temperature on the y-axis and not on the x-axis?
Why the temperature, it is on the x-axis here. You're asking about this figure.
Yes, so sorry, my mistake. Why is it on the x-axis and not on the y-axis?
Well, why should it be on the y-axis?
No, it's just like I saw X on the y-axis and T on the x-axis, and I guess I was a little bit confused as to what was actually going on here.
Yeah, and there's no, how can I say, there isn't any guiding principle about this. There isn't, if I can say, it won't change what we can see. We could have chosen to plot these graphs the other way around. We'd just be looking on different sides of this plane. So by the end of the day, we are going to consider how to navigate this plane. So yeah, you could have swapped these around, but the convention for the so-called isorate plane, as we see, we'll call this, it's to have X here and T there. So there isn't anything as yet, nothing in what we've said so far tells us there's an issue with doing it this way around, or that there's an issue with doing it the other way around. So it's just, we can just call it our choice for now, right? Okay. So we've got we've got this line, which we now know we want to avoid. And then we can think about, in our reactor, where do we actually start operating? Well, if we think about an actual reactor, so like a CSTR or a PFR, whatever it is, we know that when we enter the reactor, we are entering with a zero conversion. So we are somewhere along this line. And then it depends what the entry temperature is. So if we have a little mouse here. So if we have this as our inlet, as our feed stream, and we have here T in, and just for both these T in, then we can say that's my starting point. There's my T in. So I've got a T in here, and my conversion, I'm of course starting with a conversion of 0. So that's my inlet temperature. Then the other thing I have is my energy balance. Right, my energy balance tells me, this thing keeps coming up. My energy balance tells me, okay, yep, this. Okay, let's just look up an energy balance here. So my energy balance, well, not even that. My adiabat, let's just say my adiabat. So let's say we have a reactor operating adiabatically. Then we know we have this equation. So conversion is changing linearly with temperature, and the gradient of the line is this. So if you look at this equation, it's telling us that x is linear in t. So this is going to be a straight line when we plot x versus t. And it's going to have this gradient. Or if you want to be more strict, dx dt is equal to this thing, right? And if you think about this, if you have pure A, as we saw many times, this is just CPA, and this is nothing but the heat of reaction. So these are two constants. So this is a very easy gradient to identify. And this is how our reactor operates. We said as the temperature rises, then our conversion changes. So if we plot this line, we'd get something like this. So let's just do a straight line here and see if that. So we said that's our inlet point. And so our line is doing this, right? Now, that is in effect, we are looking at different volumes of reactor. So if this is a CSTR, if we consider a point here, then our conversion and temperature have, the reactor is only big enough to get us to this point. And then as we move closer to this line, remember this is the line where the reaction rate is 0, we can imagine that we need bigger and bigger reactors here. And we'll in fact see later that down here, maybe your reactor is quite reasonable. Maybe it's only 2 cubic meters here. And over here, you'll need something like some crazy numbers like 5 million cubic meters, right? Crazy sized reactors here. So as you move along this line, you are encountering different reaction rates. And but we can't really see that on this plane as yet. So let's go back to what we did, right? We got this line, and now this is us chugging along with our reactor, right? This is, if you like, this is the human effort down here. This is us with our little reactor. And here's nature with this line. Nature is saying, hang on, you can't keep going. Here's equilibrium. I'm stopping you at equilibrium here. So we are trying to react and convert, but nature says, no, just stop right there. So what we want to do then is to think about, well, if that's the limiting point there, what are the rates on this plane? So to do that, let's go back to our development. Yeah, in this chapter here. So we had found that line by deriving this, right? And by the way, please do this exercise. So there are a couple of exercises. If you look in the Dropbox folder, there is all the tutorial questions are there. So do take one of those problems. It gives you the function for Kf and Kr, Arrhenius functions. Choose a set of temperatures. That will give you a set of Kfs and Krs, calculate Ke, use that to calculate Xae, and plot Xae versus T, and see that you get that kind of curve that we drew just now. So you'll get that, and that's the equilibrium. So that's at equilibrium. This is a special line where we know the reaction rate is 0. Then we say, if we're going to draw this, why don't we draw lines where we want to operate? And there's nothing to stop us doing that, because when we did this, when we were at this, when we took this balance, we arbitrarily chose to look at the 0 state. We said at equilibrium, R is 0. But we can choose other values if we want. There's nothing to stop us just saying, I want my reaction rate to be 10. If R is 10, then what do I get? And that's what we're saying here. Let's go back to this equation and let's keep this. Let's not zero this off. We want a nice reaction rate, so we might as well keep this. And then we can see here Ca naught, so we might as well divide by Ca naught. And then we've got the Kf. So let's group out the Xa's. We can see Xa's here. So let's move this Kf onto that side. So Kf plus that. And then group the remaining Xa's here. So you can see Kf plus Kr. I can see I've got the wrong sign here. 1 second. Let's just correct this. So this one is a plus. Right, so we can see here we have okay, here did not correct that. I think I need to clear my cache. Yeah, okay, so that's what we have here. And so we regroup for Xa, and then we solve for Xa, and we get the form like this. And now we can plot this line. So we can pick a reaction rate, the reaction rate of interest to us. We can just pick a 10 if we wanted. And then we've got a series of T's, right? T is on the x-axis. So we can calculate a series of K's, Kf's and Kr's. So we can calculate the values here as a function of temperature. And my apologies on this, I didn't get to drawing the graph, so I'm just going to refer to the notes. So in the notes, I've got one plotted. So first off, here's our equilibrium line. R is 0 on that line. And here you can see R is 10 to the minus 5. So there's a little line down there. And then if R is 10 to the minus 6, then there's another line there. R is 10 to the minus 7, there's a line, and there's a line. So you can see all these contours of non-zero reaction rates. And along these lines, R is fixed. So it might seem surprising to you that this nice algebraic looking equation is so curvy. But that's because, remember, behind these little k's here, we've got Arrhenius expressions. And these are all Arrhenius, but they've got very different constants. So this is actually much more nonlinear than you think when you factor in the Arrhenius expressions. This is just a fixed number. We always fix this number. So like you saw here, we fix an R value, and then that will give us a different curve each time. So that's how we get X as a function of temperature. So we've got a curve. So we fix an R. That gives us a conversion as a function of temperature. And that we call an isorate line. So because the reaction rate is a constant number along this line, we call this an isorate line. So this is a plane of isorate lines. And if we look at these lines, we can see that the reaction rate is the highest here. So even though this is just 10 to the minus 5, that's still high when compared with these other ones, right? You've got 10 to the minus 6, 10 to the minus 7, and so on. So we would think, well, when we design our reactor, we must try to stay close to the high rate regions, and we must stay far away from the low rate regions. So we are going to navigate this plane by creating a design. So when we talk about navigating a plane, that means we are going to choose a set of reactors. Remember, I think it was even in week 1, we were talking about a CSTR followed by a PFR followed by something else. So we are free to put a set of reactors in series one after the other. And as we do that, we'll find we move around this plane in different ways. But there is a way to pick our way around this plane such that we get a good choice, such that we accomplish high conversions in the face of a limiting reaction. You can see here we only have a nice high rate in this little sliver down here. And as we start to progress in our conversion, we are ending up in very low rate regions. So we really have to optimize our way. We have to make our reactors sweat. We have to make them do as much as possible to give us more product. And so we want to use our knowledge of this, right? We can think of this plane as what nature is doing. So each line tells us what nature will react the components, what rate it will react those components at. And so knowing this plane, we can chug along with our little lines, our adiabats. We can try to move through this space. We want to position ourselves as best we can. So that's what we're trying to do in this non-isothermal reactor design. Any questions or comments there? Okay, so that's what we are attempting. So let's think now about, well, by the way, we drew these rates down here. What do you think happens across this line? What's happening in this empty space out here? Does just nothing exist on this side? So on this side of the equilibrium line, right, this is where we are on balance producing more B. On this side, we are producing more A. So because this is equilibrium, because it's a reversible reaction, here's where we are not converting to product. Here we are actually converting back to reactant. So we won't even bother to draw this. But we should acknowledge that there do exist points over here. If we pick an unfortunate conversion and an unfortunate temperature, if it ends up here, then that means we are going to end up in a negative rate region, in a region where we are not consuming component A. So this is the plane of everything that's possible, all reaction rates. If you pick any point on here, you can get a reaction rate. But whether it's positive or not, that's another question. How big it is, it's another question. And like we said earlier, when we design our reactors, we are basically moving in a line through the space. So let's copy this across. I think it's Shift 5. what is the, how do you do snapshots on a Mac? I Googled it just now. Shift Command and 3 is not good. I think it's Shift Command and 5. Okay. So let's copy this plane through. Come on. So let's copy this plane so we can draw on it. Okay, so let's say now we had chosen an inlet temperature in our CSTR of 300. And let's say the gradient, because of the heat capacity and heat of reaction, was like this. Then let's think about where the best place to stop would be. In fact, what I want to do is shift this line here like so, and shift this point. So can you tell me what's the best place? Right, remember, we are free to pick how far along this line we are moving. So as we pick different points here, we are effectively picking the volume of the reactor. So if we choose a very small reactor, then we will only accomplish this conversion. If we pick a larger reactor, we are accomplishing this conversion and so on. So if we go right to the end here, that's the largest reactor and so on. So we are free to pick how far along this line we are going to move, right? Now, can you tell me what the best place to stop would be? Any takers there? What's the best place to stop on that line? Think about equilibrium for one.
So I think we should stop somewhere just before equilibrium.
So somewhere just before equilibrium. So you're saying go as, yeah, you're saying go as far as you can, but don't go so far you're very close to equilibrium. Yeah. So that's right. That is the right way of thinking. That gets us partly there. But can you identify a specific point on this line, which looks like, okay, let's be more specific. Can you identify the highest rate point on that line? Which point on this line gives us the highest possible reaction rate?
I think we can look at that line and check where maybe the gradient is a bit steep.
Sorry, where the gradient is?
Yeah, where the gradient is a bit steep, I think.
Where the gradient is steep. Well, the gradient is fixed here. We've got a fixed gradient. We've got the same gradient everywhere on this line. But let's look at the isorate lines. Remember the whole reason we derived that whole thing where we didn't let R8 be 0. We did that because we wanted to be able to draw these isorate lines. Now, if we look at these lines, we said this is the nice high rate region. The green one here is 10 to the minus 6. And then the red one is 10 to the minus 7. So this is 10 to the minus 7. That means if we are close by this line, if we are at points closer to the red line, we are closer to 10 to the minus 7. So as we move down this way, we are closer to 10 to the minus 6. So moving this way is better. So let's look at moving along this line. When you start down here, you are closer to 10 to the minus 7. So that's a low reaction rate. And as you move up here, you get closer and closer to 10 to the minus 6. So you see, I cheated a bit and I put this as close as possible. I put this as a tangent to this 10 to the minus 6 line. And then as we go past this, we are going away from 10 to the minus 6, and we're moving closer and closer to 10 to the minus 7 again. And then we get to a region where it's changing very rapidly, where, well, when I say rapidly, I mean it's decreasing very rapidly. In other words, the reaction rates here are extremely low. But here we can see at least we are getting to the highest possible reaction rate. So at this point, where this line is a tangent to this iso rate line, where our operating line for the reactor is a tangent to the iso rate line, this is the highest possible reaction rate. Any points to the left of this, and we are moving closer to the lower rate line, right? These rates are lower than this rate. Any points to the right, and we are moving closer to the lower rate line again. So this is the highest possible reaction rate. Does everyone agree with that? This point gives us the highest possible reaction rate.
Yeah.
Yes.
Okay. Any questions or comments there? Okay, so we've identified a desirable point. We can say, yeah, this is a nice place to stop. So we get a nice efficient reactor. The most efficient reactor that we can possibly get is here. And then do we want to sit down here? I mean, we still have a very low conversion here. It's only a 20% conversion. Just because it's a low efficiency, maybe we say, well, hang the efficiency, just go further here. But we see here the rate is so low, we'll need a ridiculous size reactor here. So let's say we do want to stop here. But we've got all this, the rest of this space, all these other regions. Why can't we get to a higher rate region? So what would you propose to do? Is there any way to get up here? Right at the moment, if we just make our reactor bigger, it will move slowly along this line. It will move slower and slower and slower. And then it's just stuck here. It can't go past this point. The reactor is infinitely sized here. So just making the reactor bigger is not going to help us. What can we do to get into these other higher conversion regions? What's possible here? Does anyone have a proposal there?
So I'm just trying here. Can we try decreasing the temperature anyway?
Yeah, that's right. So that's good. That's so if making the reactor bigger pushes us along this line, then what about trying to pull ourselves back along here? So if we manage somehow to pull ourselves back here, that means basically dropping our temperature. And then if we build another reactor, then it's also going to move in a line like that. So what do we do to pull ourselves back along this line here? In terms of our process, what would we do there? So let's see in the chat, there's something, interstage cooling, right? So Jaden, thanks. That's right, interstage cooling. So we should just draw what we are doing here. So let's just draw it on this space. So here, there's my little pen. So we've got our reactor here. So that's our first reactor. And that was fed in with this temperature. So call that T0 here. So that was our entry temperature, T0. And now we are going to make this reactor just big enough that we reach this point, okay? So that's what we call a T1. So if we look down here, if we just produce this point down here, we get to T1. And then it's not as if we can't do anything after that. It's not that we can only make this reactor bigger. We can add a heat exchanger here. So if we cool the stream down here, so this is supposed to be a little heat exchanger. If we cool the stream down here, then if this is just cooling, then we can say it's a horizontal line. And let's say we cool it back down like so. Right, then we are now at this lower temperature right here. And then we can build another reactor after that. So if we go ahead and draw another reactor after that, then in effect, we are, we'll have the same gradient. And now our line is looking like this. So we've got another line here. And this time, we can't see the tangency with these lines. So we don't quite know where to stop. But it's what we can do quite easily is just move this point around. Oops. So I want to grab this line. So let's say we put this this line here. We can see that the point of tangency is here. Let's say this pen is always so hard to find. So we've got a point of tangency here. So we'll just mark that. And then let's continue. Let's move this line again. So grabbing this line and moving it here. We are now here. So we found another point of tangency. So we'll mark that off. So that's here. And then we just rinse and repeat. So we move this line around because we know that's going to give us the highest possible rate. So we can see the other rate is there. So we'll just mark off this rate as well. So now we have identified desirable operating points. And what we can do is just create a curve through all those points. So let's do that here. And I'm not sure I'll get away with one gradient here, but let's try. I can't move that anymore. Okay, well, maybe something like that. Okay, so it's not perfect, but we can see all points along this red line are high rate points. Those are the highest possible rates moving along this line, right? This line, this red line, this so-called maximum rate path, this is a function of our gradient. Remember, the points we got were dependent on the gradient of this line. So if the gradient were different, this line would shift. But anyway, for this gradient, this is the maximum rate line. And so we now have a stopping point. We can say we want to stop here next. So the desirable point for us is on this line. So we would stop that here. So that would be how big the next reactor should be. And then we can repeat that process. We can add another cooler after this. So that would take us here. And then again, another reactor, and we step forward on this line. So that's how we can work our way up here. We can get to higher conversions, taking advantage of as high a rate as possible. Yeah, and that's how we can navigate this plane. So once more, we've taken advantage of what we know about nature. So nature is giving us these, these possibilities. We've observed nature enough, right? We've done our experiments in the lab, and we've put together our rate data. And Prof. Lockhart will be doing that with you in detail, taking rate data and extracting the kinetic parameters and all that. But you've got, from your rate data, you've got your ISO rate lines, and now we can use this to figure out a good criterion to choose the best reactor sizes. So that's the point of these ISO rate lines. We can design a reaction scheme. We can design how to step our way forward here and get as good as possible a reactor sequence. Any questions or comments there? Right, so if you look at what's on the Dropbox folder here, you'll find these tutorial questions. And I'm just going to skip past the first one. So the second one, it's giving us the kinetic constants that were used to generate the ISO rate lines shown here. So you've got a nice plane drawn here, but also do the exercise of just drawing these planes, right? Drawing these lines. But here we are asked to draw the maximum rate path line. So like we just described, there is a line where you can get the highest possible rates, and it is a function of the gradient, which depends on theta I, CPI, and all those things. So get the maximum rate path line, show the operating line of the CSTR, think about how you would draw a PFR, and so yeah, use that to design a system. And the criteria here, we've mentioned a few things. This criterion, which says 10K short of equilibrium, right? That's basically saying, look at where you would end up along this line. So you can move along this line, and you can identify a temperature where you would be at equilibrium. So we know we don't want to be all the way at equilibrium. So we would say, just as a rough engineering criterion, let's just stay 10 degrees away from it. So you just identify where the equilibrium point would be and step back by 10 degrees, and that would be a point. So that is a different criterion. That's where you are trying to maximize the conversion. In this case, we are trying to maximize the reaction rate. So it's our choice, right? It's our design. We are free to be as creative as we like and use whatever criterion we would like. So if we've decided we want very efficient reactors, we want the highest possible reaction rate, then we follow the maximum rate line. If we say, no, my separation costs are extremely high, so I want as high a conversion as I like, then we would say, well, let's go along this line, but we don't want to go all the way to equilibrium, because then we'll need an infinite size reactor. But if we stay at least 10 degrees away, maybe we'll get a reasonable reactor there. So, so those are different criteria. And based on what the question says, if it says your separation costs are extremely high, then you know that means we need to get high conversions, and so use the 10K line. If it says get nice small reactors, then that means get high rate reactors and use this criterion instead. So use that now to answer this question, right? So in this question, we are told to design the CSTR and the PFR, and to accomplish some overall conversion. Let's see, we want to operate the first reactor at a high rate, and we'd like to operate the following PFR of a reasonable length, which means it's not too close to equilibrium. Okay, so go ahead, take that plane. First, even just do the basic thing first. Just how do you get that gradient, right? Look at the data in the question. You'll see there isn't a heat of reaction stated here. So think about, how would you get that gradient? Look at your energy balance. how do you ever get that gradient if you don't have the heat of reaction here? Okay, so I'll give you some time to try that out. Any questions you have, please go ahead.
Wait, sorry, I just got back from something now. Do you want us to do question 2A and B right now?
Yeah, it's still a tutorial, right?
Okay.
Okay, so let's just talk about how to draw our operating line quickly. And of course, our operating line comes from our adiabat. So if we're trying to draw using our adiabat, we know the adiabat has this expression. So x equals minus, and here it's the sum. So yeah, sum I, and this is theta. Well, it's capital theta, theta sub I, c sub p I, and that divided by delta HR, so heat of reaction times T minus T in, right? So that's the equation of our adiabat. And we can see the gradient here is this. So of course, if it's pure A, then this simplifies. Oops. So this simplifies to just CPA here. So that's just CPA. So that's easy. We have the heat capacity of A, and this is just the variable on the axis. The part that's missing is delta HR. Now, if you recall from our Van 't Hoff equation, so if you go back and look at the thermodynamics, I can't remember exactly where we did it, but we had said that delta HR was equal to the activation energy of the forward reaction minus the activation energy of the reverse reaction. And if you look at the statement of the problem, we can find the activation energies, right? Here they are, 28,000 minus 49,526. That would be our heat of reaction. So hidden in this question are is the data that you can use to get the heat of reaction. So you've got the heat of reaction now, you've got the heat capacity. So that ratio tells us the gradient of the line. So once you've got the gradient of the line, you can go ahead and look at your inlet temperature. So your inlet temperature, it says the feed stream is A at a temperature of 300 Kelvin. So we've got the feed stream temperature and we've got a gradient. So that means we can draw our line like so. And with that gradient, we can go ahead and identify all those maximum rate path points. We can even identify what equilibrium point we were going to, so we can step back and find the 10 degrees line. And so we can draw all those things. And then we can decide what criteria, what approach we want to take. We could say, I want very efficient reactors, then I'll follow the maximum path line. Or we could say, I want high conversion lines, then you'll choose the 10 degrees to equilibrium point. So that's how we can do it. It's as easy as just finding that gradient. So your starting point is get that gradient, then you'll have this line that you can use to find the tangent points and the equilibrium points. And you can use that to produce the construction lines that you need to produce a design there. Okay, any questions or comments on that? All right, if not, then I think that's enough direction to complete all these questions, right? It's basically that you just have to identify those operating regions, identify those desirable regions, and so step forward and follow the criteria. So if it says we want an overall conversion of, say, 70%, then you know you need to cool and step up and cool and step up and cool and step up until you reach 70%. But of course, we have to think about sometimes if it's asking for some ridiculous conversion and you need 50 tiny little reactors to get up there, then you would question whether that's a good criterion. But that's how we do it, right? You can step up here. That will tell you the number of reactors that you need and also the size of each reactor in the train. So the next step after that is to use the material balance to determine what volume is required to achieve that change. Okay, any questions or comments there? All right, if not, then yeah, this is the type of thing that you just have to do, right? So I'm going to call it there for today. So do work through these exercises. This is a kind of the famous question in this course, so definitely know how to do this. Yeah, that's one of the key aspects of designing a reactor sequence. Okay, then I guess I'll see you on Friday.